Hello, my name is Timothy Gallagher and this is my lab for circuits and capacitors. In this lab, we'll be predicting the behavior of circuits containing resistors in series and parallel, and examining the behavior of resistors and capacitors. Through this, we will be using Ohm's law, which states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. This is described by the equation seen to the right, V equals IR, where I is current through the conductor, V is voltage across the conductor, and R is resistance of the conductor. In addition, the node rule states that the flow into a junction is equal to the sum of current flowing out. Throughout this, conservation of charges will be an important principle for future calculations, as well as the equations seen to the right and the node rule. We begin our investigation with a simple series with two 1.5 volt batteries, 2 ammeters, and 2 resistors, one of 47 ohms and one of 100 ohms. The calculations for the predicted voltage are shown here using Ohm's law, with our results of 0.02 amps matching the prediction. The graph can be seen to the right for our results. Here we remove ammeter 2 and measure voltage and current of the circuit. The voltage is 3 amps as seen on the meter, but the current is 0 because it does not flow through the meter as it did priorly with the ammeter. Here is the graph of the potential differences with the positions throughout the circuit. It is important to note that the sum of all segments sum to 0 as expected prior to our observations. Here we see a parallel series with the same specs as the prior series we observed. The ammeter has a resistance of 0, so current flows through it as opposed to the resistor, so it acts as a simple series. We obtained a measurement of 0.06 amps for this circuit. Moving on to RC circuits, on the left we have a capacitor charging, and on the right we have a capacitor discharging when the battery is removed. We will measure the time of discharge and charging for the capacitor with a light bulb of 10 and 20 ohms. Here we can see the time it took for each capacitor to charge and discharge at the light bulb of 10 and 20 ohms. With a 10 ohm light bulb, it took 7.2 seconds to charge and 9.8 seconds to discharge. With a 20 ohm light bulb, it took 13.7 seconds to charge and 19.9 seconds to discharge. Now, graphing the capacitor discharge over time, we find after plotting the natural log of the voltage over V0, we find a slope of negative 0.136. Using the equations, we find the RC constant of 7.35, which is close to the predicted of 6, with the equation seen to the bottom left. Here we can see the data in the middle that was used and the graph to the bottom right, as well as the trend line that was calculated. The top right shows how the data was collected. Now moving on to the discussion. What if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it have affected the circuits you hooked it up to? We would find that the current reading in real life would be lower because actual ammeters have resistance, as opposed to the simulation where the ammeters had no resistance. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Ideally, the battery would charge immediately, but again, there's resistance in real life, so this would require time. Thank you. This has been my lab for circuits and capacitors.